This week we introduced a fundamental measure of geometric measure theory, the Hausdorff measure. We'll actually present a more general method for constructing measures called the Caratheodory construction, from which Hausdorff measure is a special case.
So, as a motivating example for the definition of the Caratheodory construction, let's go over the definition of Lebesgue measure. So, suppose we have a subset A of the plane, and we would like to estimate the area of this set. So, one way we can do this is by approximating it by sets whose areas we can easily compute. So, for example, squares. So in this figure over here, I've covered the original set A by a union of squares. And so the sums of the areas of these squares give me an approximation to the true area of A. However, notice that the sum of areas is always going to be an overestimate of the set A. It's always over because these squares, of course, contain the set A, but it's going to be strictly over usually, especially if the set is totally disconnected, because as you can see in these squares, the squares also cover a lot of empty space that's not necessarily inside the set A. So instead, what I do if I want to compute the Lebesgue measure of A, so let's say two-dimensional Lebesgue measure of A, what I do is I take the infimum over all such coverings. So I take the infimum of the sum of the area of some qi's, where the qi's are some squares whose union contains A. Okay, so when we define the Caratheodory construction, the definition is going to look very similar to what I have here, in the sense that the main ingredients are a collection of sets that I wish to approximate a set by. So in this case, I picked squares, and then a function that tells me how I'm going to weight each set in my collection when I approximate my set. So in this case, I decided to define the weight of each square to be its area. Now, the Caratheodory construction also has an additional feature, and for that I'm going to go over one more example. So suppose I want to estimate the length of a curve. So let's call this curve gamma. Okay, so one thing that I could try is coming up with a similar definition like I did up here. So instead of cubes, I'm going to use balls since they're a little easier to draw and work with. So I'm going to find a function L of gamma is equal to the infimum. Okay, so because it's a curve, I'm not going to sum the areas of the balls. I'm going to sum the diameters of the balls. I'm going to infimize over all coverings of gamma by balls. Okay, so this, however, will not give me the true length of the curve gamma. And the reason why, which is a little stupid, is the collection of balls that will give me the infimum for this is actually just a collection of one ball. If I just contain this curve inside a ball whose diameter is equal to the diameter of the curve. Okay, so why this is clearly not the length of the curve, because we can see that the curve winds on itself inside the ball, and that it's definitely longer than the diameter of the curve. Okay, so why did this not work, this definition not work here, but the definition worked when we considered Lebesgue measure up here? Okay, well, one reason is that when we compute the Lebesgue measure, okay, we took the infimum over all coverings of a set A by squares, and then over all such coverings, we infimize this sum here. Now, if we take a sequence of coverings so that the sum of the areas of the squares in the covering converges to the infimal value, the squares in this collection will necessarily get smaller and smaller and smaller and become better and better approximations of the set A. Now, in the second case, when we're trying to estimate the length of the curve gamma, when we take an infimum over all balls covering the set, the balls don't have to get smaller. So in fact, the covering that infimizes this is just one very large ball. However, if we wanted to get a true estimate on the length, really what we want is to use small balls, because when we add up the length of small balls covering our curve, or add up the diameters of these balls. So you can see in this picture, for example, if I were to sum up the diameters of these balls, they would be closer to the true length of the curve gamma than if I use this large ball. So what this means is that if I want to define a set function, if I want to define a measure that is going to return the length of this curve, I somehow need to force the sizes of these balls to go to 0. So instead what I do is the following. I'm going to alter this definition here. So I'm going to let L of, I'm going to put a delta there, where delta is some positive number. And then I have the same definition, except now I'm infimizing over all collections of balls covering my curve, but such that the diameter of the balls are less than delta. Okay, so this gives me some new measure. And what I do then is I define my final definition of length to be the limit as delta goes to 0 of L of delta gamma. Okay, so in fact, the role that delta is playing is that as delta goes to 0, and I'm forced to take coverings by smaller and smaller balls, that forces my coverings to pick up on some very small scale fine features of the curve that might not have been detected if I had only covered by large balls. The Caratheodory construction goes as follows. So suppose we have a metric space, a collection of subsets of X called F, and a non-negative function defined on these sets called H. H is sometimes called the gauge function. We'll also make the following assumptions. So first of all, we'll assume that for any delta, we may find sets from our collection that cover the whole metric space and whose diameters are all less than delta. We'll also assume that for any delta, we can find sets inside our collection whose H value and whose diameter are both less than delta. Or in other words, we can make these values as small as we wish. We now define the following function for positive numbers delta and for subsets A of our metric space. So psi delta of a set A is equal to the infimum over all coverings of A by sets from the collection E whose diameters are less than delta. And over all such coverings, we infimize the sum of the H values of these sets. So a couple of comments are in order. So first of all, observe that 1 implies that this set that we're infimizing over is non-empty. So the reason why is that 1 says that we can cover our metric space X by sets whose diameters are all less than delta. So in particular, such a covering will be a covering of the set A, and thus this set here is non-empty. Secondly, item 2 says that psi delta of the empty set is 0. So the reason why is that if A is the empty set, then any collection of sets is a covering of the empty set. So in particular, any one set from our collection F is a covering. So in this case, the psi delta of the empty set is just the same thing as the infimum over H of E, as E ranges over all sets in my collection that have diameter less than delta. And 2 says that I can pick those values as small as I want. And so thus the infimum is 0. So here's the definition of psi delta again for reference. So it's not too hard to show that this is a measure in the sense that it gives 0 mass to the empty set. It increases as the set A increases, and it's also countably subadditive. Now, as delta goes to 0, observe that this function is going to be increasing. And the reason why is that if I look at this set right here, as delta goes to 0, there are fewer and fewer collections of sets EI that satisfy these properties, and hence the set is getting smaller, so the infimum must be getting bigger. So because it's an increasing function, that means that when I take the limit as delta goes to 0, this sequence of measures will converge. So in the end, I define a function psi, a set function psi of A, to be the limit as psi delta goes to 0. The limit of psi delta as delta goes to 0. And because these psi deltas are increasing as delta goes to 0, this is equivalent to just taking the supremum over all deltas. So this function psi now gives us the measure that we want. So for collections of sets F, set function H, and for psi defined as above, the function psi is actually a Borel measure. And in fact, if the collection F consists of Borel sets, then the measure psi is in fact a Borel regular measure. So I won't prove this here, but this is a really good exercise to go through yourself. And the hint is to show that the measure psi is actually a metric outer measure. So using the Caratheodory construction, we can now define what Hausdorff measure is. So for Hausdorff measure, we take our collection of sets F just to be all subsets of the metric space. And then our gauge function H, we're going to let it be the diameter of a set to a power S. All right, so then for delta bigger than 0, and for S non-negative, we define the H delta S measure of A to be the Caratheodory measure using this gauge function and our family of sets, which is just the power set, the set of all sets, which simplifies to this definition. It's just the infimum over all coverings of A by sets of diameter less than delta, and over all such coverings, we infimize the sum of the diameters of the sets EI to the power S. And then finally, the S-dimensional Hausdorff measure of a set is just the limit of these H delta S functions as delta goes to 0. We now go over a few useful properties of Hausdorff measure. So first of all, the zero-dimensional Hausdorff measure is just counting measure. Secondly, Hausdorff measure in Euclidean space satisfies the following homogeneity property. So for a number t bigger than 0 and a subset A of Euclidean space, if we define T of A to be the set of all multiples of things in A, so TA is the set of T times X where X is in A, then the Hausdorff measure of TA is equal to T to the S times the Hausdorff measure of A. Hausdorff measure in Euclidean space is also translation invariant. So if I have a set A in Euclidean space and a vector X, if I look at the translation of A, so this is a set of X plus Y, where Y is an element of A, then the Hausdorff measure does not change under translations of the set A. Finally, in the case of d-dimensional Hausdorff measure in RD, Hausdorff measure coincides with Lebesgue measure up to a specific constant. So they're actually just a multiple of each other. In fact, one can show, however it's a bit complicating to show, that the constant here is just 2 to the d over the Lebesgue measure of the unit ball. So in fact, we get the following very easy formula for the Hausdorff measure of a ball of radius r. It's just the diameter of that ball to the power d. Hausdorff measure also plays nicely with Lipschitz functions. So recall that a function f between two metric spaces is L Lipschitz if f expands the distance between points x and y no more than a factor L. And it's by Lipschitz if its inverse is also Lipschitz. Then we have the following theorem that if f is a Lipschitz map from x to y, then the s-dimensional Hausdorff measure of f is no more than L to the power s times the original Hausdorff measure of A. So this is a sort of easy exercise that will give you some practice working with the definition of Hausdorff measure. So a lot of times we're not actually concerned with the exact value of what the Hausdorff measure is of a set. Often we're actually concerned with whether or not a set has Hausdorff measure 0 or not. And the next lemma gives a few equivalent definitions for when a set has measure 0. So for a subset A of a metric space and some number s between 0 and infinity, we have that the s-dimensional Hausdorff measure is equal to 0 if and only if the hs delta measure of A is equal to 0 for any delta, if and only if the hs delta measure is 0 for some delta, and this is true if and only if for any epsilon we may find sets covering our set for which the sum of the diameters of these sets is less than epsilon. So to see an example of how we work with Hausdorff measure in actual proof, we'll actually go through the proof of this lemma. So first of all, notice that some of these implications are immediate. So first of all, 1 implies 2. So recall that hs is equal to the supremum of hs delta over all delta bigger than 0. So if hs is equal to 0, then that implies that hs delta is 0 for all delta. Furthermore, if HS delta is 0 for all delta, then clearly it's 0 for some delta. And finally, so if it's equal to 0 for some delta, then by definition of HS delta, that means that we can find a covering of A by sets EI where their diameters are less than delta, and so that the sum of the diameters to the power S is as small as we wish. And that's exactly what 4 says. So what we'll focus on is showing that 4 implies 1. So first of all, notice that without loss generality, we can assume that S is bigger than 0. And the reason why is that in the case when S is equal to 0, the only way that we can make this sum as small as we want, where S is equal to 0, that's only possible if the set A is the empty set, in which case clearly the zero-dimensional Hausdorff measure will be 0 for that set. So we'll assume that S is a number bigger than 0. All right, so let delta be bigger than 0. By property 4, we know that there exists a collection of sets EI such that they cover the set A, and also the sum of their diameters to the power S are less than delta to the power S. Okay, so notice that S is bigger than 0. So as delta goes to 0, delta S is going to go to 0. Now notice that because this sum is less than delta S, that means that each individual member of this sum is less than delta S. And so that implies that the diameters of each EI must be less than delta. Okay? And so thus, recall that the HS delta measure of A is equal to the infimum over all sums of this type over all coverings of all coverings of A by sets with diameter less than delta. And so that means the HS delta measure of A is going to be less than or equal to the sum of the diameters of EI to the power S, which by assumption is less than delta S. And so thus, taking the limit as delta goes to 0, sorry, this should be a D or an S. So the HS measure of A is equal to the limit as delta goes to 0 of the HS delta measure of A, which is equal to limit as delta goes to 0 of, or is less than or equal to, delta S, and that is equal to 0. And that is the proof that 4 implies 1, which completes the chain of implications. It's useful to know that in the Caratheodory construction of Hausdorff measure, we could have picked a smaller class of sets than just a class of all sets. So indeed, if we let the gauge function h be the same, so notice that this gauge function is a function of t. This is shorthand to say that hs of E is just a function of the diameter of E, and that function is just the diameter of E to the power s. Okay? So if we use the same gauge function as before, but instead use either the class of open sets or closed sets or convex sets in the case of Euclidean space, then it's not too hard to show that the resulting Caratheodory measures that we get are all still equal to Hausdorff measure. Now, if instead we use smaller families like balls or cubes in the Caratheodory construction, then we don't get Hausdorff measure back, but we do get measures that are comparable. So for example, if we perform the Caratheodory construction using the set of closed balls as our collection of sets, but use the same gauge function h sub s as before, then we obtain what's called the s-dimensional spherical Hausdorff measure. And it's not hard to show that this is comparable to Hausdorff measure, and in particular satisfies the following inequality. Now, if we instead use dyadic cubes, we get the s-dimensional net measure, or dyadic Hausdorff measure. And one can show similarly that the following inequalities hold, and it's comparable to Hausdorff measure. Now, why did we not use these sets in the first place for defining Hausdorff measure? Well, first of all, estimating Hausdorff measure is a bit easier by using all sets, since we can use any sets in our cover. We're not restricted in which ones we can use. Secondly, the definition is consistent across metric spaces. So note that whereas the dyadic Hausdorff measure requires dyadic cubes. Finally, notice that Hausdorff measure is rotationally symmetric. So this follows from the earlier theorem about estimates for Hausdorff measure under Lipschitz maps. Since every rotation is an isometry, meaning that it's 1 by Lipschitz, that means that it preserves measure. However, one can show that the dyadic Hausdorff measure is not rotationally symmetric, since, and this is because the dyadic cubes are fixed. We can't use rotations of dyadic cubes. We're always using dyadic cubes that have edges parallel to the axes. So, as an example, suppose we consider let's say a subset of the real line going from 0 to 1. Okay, so one can show that the dyadic Hausdorff measure of this line segment is equal to 1. However, if I take this line segment and I rotate it 45 degrees, and I look at this new line segment, that's actually going to have a different dyadic Hausdorff measure. And the reason why is because when the coverings by dyadic cubes, the number of dyadic cubes essentially that I need to cover this line segment, because I can align them along the diagonals, those are fewer than the number of dyadic squares that I need to cover this line segment. Okay, so the rotated segment is actually going to have smaller dyadic Hausdorff measure than the line segment that makes an angle of 0 with the x-axis. However, the dyadic Hausdorff, each of these measures, so spherical and dyadic measure, are useful in some particular context, which is why they've been defined. So finally, you might be thinking about whether there are other sort of interesting Caratheodory constructions using gauge functions other than the diameter of a set to a power s. And the answer is yes, there are many examples. My favorite example is the following theorem due to Makarov. So his theorem says that there's a constant c so that the following holds. So first of all, a few definitions. So suppose that we have a simply connected plane in the domain. Okay, then recall that the Riemann mapping theorem says that there is a conformal mapping from the unit disk onto omega. And one can show that it extends continuously to the boundary as well. Now, let omega denote the push forward of the normalized length measure on the unit circle. So the resulting measure is a probability measure on the boundary of omega. So this measure is called the harmonic measure of the domain omega. Then one can show that the harmonic measure is absolutely continuous with respect to the Caratheodory measure that uses all subsets of Euclidean space as its collection of sets, but uses a gauge function h, where h of a set A is equal to big H of diameter A, where big H is this crazy function, t times the exponential of c of root of log 1 over t log 1 over t. Okay? Moreover, this result is tight in the sense that there is a smaller constant c, so that the corresponding Caratheodory measure is singular with respect to harmonic measure for some simply connected planar domain. In particular, as a corollary, since this exponential function here times t decays so slowly in t, this function is at most a constant times t to the power s for any s less than 1, at least as t goes to 0. So this implies that harmonic measure is absolutely continuous with respect to any s-dimensional Hausdorff measure for s less than 1. However, this theorem is more precise than that statement, in that it says in some sense that there is an intermediate dimension that lies between dimension 1 and every other dimension less than 1, with respect to which harmonic measure is absolutely continuous with respect to each of those, each Hausdorff measure for each of those dimensions.